Good everyone. Today we're going to be looking at hybridization of atomic orbitals. Hybridization of atomic orbitals. Now, hybridization means the hybridization of atomic orbitals is the mixing of atomic orbitals, which are s and p orbitals, d orbitals, and so on, to form a set of new orbitals that we now call hybrid orbitals. Hybrid orbitals. So the major hybridization we're going to be looking at in this chapter is the sp² hybridization, sp² hybridization, and the sp hybridization. Those are the three hybridizations we're going to be looking at as far as this class is concerned. So please ensure you subscribe to this channel and turn on our notification bell. Don't skip any part of this video in order to get the full details of everything we're going to do in this place today. So let's move on to the main class. Now, let's go with this first one. We'll go with this first, which is the sp² hybridization. Now, what is the meaning of sp² hybridization? Now, sp² hybridization means a type of hybrid orbitals, that is formed from the combination of one x orbital and 3p orbital. That is what forms the sp² hybridization. So, if we want to say that, we cannot say that we have just one of x and have 3 of p. So if we have 1 of x and we're having 3 of p, okay, we are now having total of 4. So the total orbitals present will be 4 orbitals. We have 4 orbitals there. And we're having what is the fraction of x, or the percentage of x orbitals inside this sp² hybridization. The result of x will be the number of x. How many x do we have here? So we have just 1 x. We have 1 of the x divided by the total number. What is the total number? The 4 times 100%. So this is going to give us 25%. So the full orbitals, which is the sp² hybridization, contains 25% of x. So we have 25% s character. Has 25% s character. Please, you take note of that. Then let's check the percentage of p that's present in this place. Okay, if I want to get the percentage of p, since we have just 2 of them, the s and p, the total will give us 100%. You can just remove this one from 100. We are going to have 100 minus 25. We are going to have 75%. So let's check and see if we can also figure it out. The value of p orbitals there will be, how many p do you have here actually? We have 3p. So the total p is 3. How many orbitals do we have in total? We have 4 of them over the total, which is 4 times 100%. So this is going to give us 75%. That's what we're going to have. So this orbital has s character to 25% and p character to be 75%. So there are other properties this orbital also have, or compound that possesses this hybridization also have or exhibit. Now, one of them is the bond angle of this hybridization. Let's say, for example, a compound that has this hybridization. Example of this compound is the molecule of what we call the methane. The methane molecule has is a typical example of a compound that have this hybridization. And the molecular formula of this methane is CH4. That is the molecular formula, CH4, just composed of 1 carbon and 4 hydrogen. 1 carbon and 4 hydrogen. So what I'm going to have here. So how do we actually show this out? Now the bond angle of this carbon here, since it's sp² hybridization, we're going to show it. We're going to show it. Since sp² hybridization, this carbon is sp² hybridized. The bond angle of this carbon will be at angle 109.5 degrees. That's why we're going to have 109.5 degrees. That is the bond angle of the carbon atom that is sp² hybridized. Then the shape of this molecule, since the shape of molecules that are sp² hybridized, the shape is tetrahedral, have a tetrahedral shape, and other show out how is this one actually, how this hybridization is actually. So let's see what we have. Now, the carbon at ground stage has 6 electrons in the, if you look at the share of carbon, we have 6 electrons in total. The atomic number of carbon is 6. So, if I want to draw the electronic configuration, we are going to have 1s2, 2x2, and 2p2. 2p2. Remember, x orbital can take maximum of 2 electrons, then p can take maximum of 6 electrons, and so on, while doing the electronic configuration from the outbound principle. So the next thing we're going to do here now, okay, let's try and represent this in the Hund's rule. Now from Hund's rule, you can just draw for the x orbital, we have 1x2. So you put the 2 orbitals here, and the one spine in opposite direction. From Pauli's exclusion principle, that no more than 2 electrons can occupy an orbital, and if they do, they must spine in opposite direction. So this 1s2, then let's go to 2x, 2s2, it should also be 2, but spine in opposite direction, as 2s2. Then we have 2p6. But what we have is 2p2. So P can contain maximum of 6. So you have a space that contains 6. But we cannot put 6 electrons in just one orbital, because no more than 2 electrons can occupy a single orbital. And even though they do, it should spine in opposite direction. So what we're going to do, we're going to degenerate this into 3 equal parts. We'll degenerate it or divide it into 3 equal parts. So to form a degenerate orbitals, and this one will be 2px, this one will be 2py, so that will be 2pz. That's what I'm going to have. Now, this 2px orbital is just something like this. We're having something like this. What we're having. The 2px is just along the x-axis and is dumbbell in shape. That is 2px. The 2py is along the y-axis and is dumbbell in shape. And the 2pz is along the z-axis and is also dumbbell in shape. That's what we're having. This one is 2px, this one is 2py, this one is 2pz, 2pz. That's what we actually have. So this is what we're just that is shape, the 2px, 2py, and 2pz. So the next thing we're going to do, let's distribute this 2p and 2 electrons that we have here now. So it is not good to just come and say we have 1 and 2, because from Hund's rule states that electrons are distributed singly in orbital before pairing. So if you want to share electrons into an orbital, you're probably going to share them singly before you start pairing. So from that rule, we're going to share these 2 electrons inside this orbital singly first. Then that is all. Now, there is one. I said, okay, if we now want to hybridize this, we're going to excite this part of this carbon. We're going to assign this carbon, in which one of these electrons will fill up this existing or the remaining space of this 2p, both 2px and 2py. So next thing, so this is already having, like what we have here now, what we need for this hybridization. We need just one x orbital. We need one x orbital. I have one x orbital already. So this one is now 2x1. That's now 2x1, 2ps1, py1. There. So this what we need in this orbital to form this hybridization. We need just one x orbital. We have it. And now we need 3p orbitals. We have 1, 2, 3. So from here, from this place now. So see, we already have one electron. We can use hydrogen atom to pair everything. Remember hydrogen, we have 4 hydrogen also inside this melting molecule. We have 4 hydrogen also. So hydrogen is around the carbon. You can just put hydrogen around this. You can say, okay, this one is the carbon atom, and put hydrogen around it. So hydrogen can come and fill up this. So hydrogen has just one x1. That is hydrogen for you. That is the configuration of hydrogen. So one of these x orbital can come and stay here. You don't fill up this, the next one fill up this, next one fill up this. So we have just x and x will give us sigma bond. Then x and p also give us sigma bond. X and p will give us sigma bond. S and p will give us sigma bond. So how many? We are going to have 4 sigma bonds in this compound is CH4. So how many bonds do we have? Let's actually check. So we are having C, H, H, and H on H. So how many sigma bonds do we have there? We are having 1, 2, 3, 4. So we are having 4 sigma bonds. Okay, we are seeing there. So X and P orbital will give you a sigma bond. X and X orbital will give you a sigma bond. Because sigma bonds are formed by the head-to-head linear overlap of atomic orbitals, both X and P orbitals. While pi bond, there's another bond called pi bond that will be coming from the next one we're going to look at now. Pi bond is formed from the side-to-side literal overlap of just P orbitals only. So P orbitals give us pi bond. So that's what we're going to have. So this hybridization now, what exists here, we used 2x, we used 2px, we used 2py, we used 2pz to salvage this issue. So this is how we have. So we can ask you the orbitals, these are the atomic orbitals that was involved in this sp² hybridization. So the next thing we are going to look at briefly will be how to round up this sp² hybridization. That's the next thing, how to run through that sp² hybridization. So let's go to the next example, is sp² hybridization. sp² hybridization. Now there are some characteristics of this. Okay, without any further delay, we can say sp² hybridization is a type of hybridization that has just one s orbital. We have one x orbital here, one s orbital, then we have 3p orbitals. We have 3p orbitals. No, just 2p orbitals. We don't have p2. So this will be 2, not 3, and 2p orbitals. So let's check and see what we're going to have. So let's check the percentage of x and p that will be there. So the total orbitals will now be 1, 2, that's 3 already. So the percentage of x in that place will be 1, because we have just one x over the total, which is 3 times 100%. That's 100%, and that's going to give us 1 over 10 give us 3.3333. So let's leave it to 2 decimal places. We will have it as still 33.33%. So we will have 33.33%. The percentage of p that will be there will be how many p? We have 2p over the total 3 times 100%. So this is supposed to give us 0. Times 100 give us 67.6666. Let's do the decimal place. We have 66. So this over this will give us 66.666, something like that. So if you just run through everything, we will have 66.67% to 2 decimal places. That's what we have. So this is the value of p inside this sp² hybridization, and this is the value of x in this sp² hybridization. So the shape of this hybridization, the shape is triangular. You have a triangular shape, and you don't need 1x and 2p orbitals to run through this. Example of a compound that exhibits in the hybridization is the ethyl molecule or ethylene molecule, and the formula is C2H4. We use something like this: C, CH, and H. Also have H and H. So you see this carbon is already bound to this carbon, and we have 2 bonds here. One of them is a sigma bond, the other one is a pi bond. So if you have just a single bond between 2 atoms, you can tell it to be a sigma bond. But if you have double bond or triple bond will give you 1 sigma bond, 1 pi bond. Triple bond will give us 1 sigma bond and 2 pi bonds. Sigma bond can only exist as 1 with 2 atoms, but pi bond can exist more than 1. Yes, we have 2 sigma and 2 pi bonds. But if you have just 1 bond with 2 atoms, it must be a sigma bond. Please take note of that. So let's try to hybridize these 2 carbons to see what we are going to have. So what we already have, carbon in this excited state, we said is this 1s2, 1s2. We have 2x2. Then we have 2p2. in which we divided this, we divided orbitals with 2px, 2py, 2pz, 2px, 2py, and 2pz. So what are we going to have here now? We are already having so you share this singly, and in this excited state, this is going to come to this place. The energy is going to drop closer down to the P, down to the X, because you don't have a percentage of S, the percentage of S, and you have a larger percentage of P there. So this is the diagram in the excited state for the carbon. And how many carbon do we have there actually? We have 2 carbon atoms. We have 2 carbon atoms. So you can draw exactly the same thing like this again for this second carbon. And do exactly the same thing for this second atom. So let us face this first. Let's face this first. So this x orbital, this s orbitals here can combine with the x orbital here to form a sigma bond. Because if 2 s orbitals combine, they are going to form a sigma. Let us draw it out. So we're going to see how for the second one. We will have this in the excited state. We will have this. Then we are going to have this. We will have this. So this one we will see how in the excited state. So we have just 5 hydrogen. So we can put 1 hydrogen here. Put 1 hydrogen here. Put 1 hydrogen here. 1 hydrogen here. Then this is the central bond. This is the central bond. These and this can combine to form a bond. This is 1x, 1x, this one is, and this one, this and this combined can just give us one bond, which is bond between 2 carbons. Because we have 2 carbons here. So this is a bond between 2 carbons, not carbon and what do you call it? Carbon and hydrogen. This will act as a bond between carbon and carbon. And it's going to be sigma bond, isn't that? This is x and x. S1, S2, 2x1, 2px1. And remember, the second bond is not x, it's not p orbital, it's hydrogen this thing, which is 1s1. So, and the other one, we have 2py1. Then this one, these two, they are not hybridized. So we call them unhybridized orbitals. This is 2pz. So this and this will overlap to form a pi bond. These two will combine to add at the central, that is these 2 carbon atoms will combine to form a sigma bond there. So this hydrogen and carbon is going to form sigma. That is hydrogen and carbon, that is s orbital and p orbital is going to form a sigma bond. So form sigma bond, sigma bond, sigma bond. Then this and this will overlap to form a pi bond. So if you still draw the structure out, remember I already showed you how to draw these structures. You draw the structure of the 2 carbon, maybe you should situate the 2 carbon in one place. So these two, remember we have a carbon-carbon bond inside. That is very good. That is very, very important. We have a carbon-carbon bond. So if I draw this for this first carbon, you draw something like your sp², your pz, then px, and pz. Then you draw for the second carbon. Then ensure the 2 carbons are situated together. So they are situated together with each other, attached to each other. In which, okay, we cannot take it half. We don't take half of them. Just take half of each. We cannot take half of each. That's the first one. Then for this is the first carbon. Then for the second carbon, which is still here, then join together. You can just drop the second carbon. Let's see for the second carbon. We will have for the pz, px, then py. So these 2pz, okay, let me draw the pz to this place. Let me take the py to this place and bring the pz. This one is very somehow technical. That's why I don't use this. So this 2pz, this one is the py. This one hydrogen is going to join this, which is 1x1. Then this one is 2py. They're going to combine with 1 hydrogen atom. It's empty here, it's empty here, it's empty here. Then these 2 will now overlap to form a pi bond. Then this central carbon will bond to that y sigma, which is x and x orbital. That's what I'm trying to explain here. But I don't use this diagram, I don't use this, but this one is more simpler and it's very easy to me. So these two are going to just give the carbon-carbon bond, which is what you are seeing here, carbon-carbon bond. Then carbon and hydrogen is what you are seeing here, two carbon ice. So what actually is bonding this hydrogen and carbon is the 2PS2Py. 2PS2Py for the second carbon. The last one, which is unhybridized, we overlap together to form the second bond, which is the pi bond. So when you check whether it's correct, we have pi bond here, we have sigma, we have sigma, we have sigma, we have sigma, we have sigma. So 1, 2, 3, 4, 5 sigma bond, 1, 2, 3, 4, 5 sigma bond, 1 pi bond, 1 pi bond. You can see the thing is actually accurate in a way. So you can also decide to say, okay, let's look at sp². Let's look at sp² now. Let's look at sp². Okay, before we look at sp, let's look at sp. Now let's look at other properties of this hybridization. Now this hybridization is still having a shape that is triangular, in case you don't know. And the bond angle of this carbon is hydrogen. The bond angle is 120 degrees. That is the bond angle. It's not 109.5. The bond angle is 120 degrees. Please take note of that. It's very, very, very important. It's very, very important. Now, there is still a way of determining, which I will look at later, just introduction to how to calculate hybridization inside the structure. I will look at it in a way. Okay, because before I look at a lot of time, then we look at sp hybridization. Then look at sp hybridization. We also go look at the unity of x, the unity of p to 5%, and so on. So we look at example of the sp hybridization. So x hybridization, we have just one x, we also have one p. You can see it. 1 plus 1 gives us 2. So the percentage of x will be 1 over 2 times 100%, that's 50%. That will give us 50%. So it's still 1 plus 1 over 2 times 100%, that will give us 50% of p. So it's equal. So when they are equal, that means we have equal number of x and p. Present is this. So I will do it. So example of molecule that exhibits this sp hybridization. Example is just an ethyl molecule. The ethyl molecule, which is our C2H2. If you want to draw the structure, you have C, triple bond, CH and H. This is you have a carbon-carbon bond here. 3 of them. Carbon is going to bond with each other 3 times here. But one of them must be a bond between X and P for carbon only, or not. Please try and understand this very well. We have 3 bonds between carbon and carbon. That's what I'm saying. So I'm going to draw 2 carbons out first. Okay, let's just draw it. You already know how to draw it. Let me say I'm drawing 2 at the same time. This one is for the first one, the second one. That is this. So I'm drawing the second one this way. So that's this 2x2. I'm going to have this. I'm going to have this. So for the second carbon, the third one, I'm going to have this third one. So this is the 2px, 2py, 2pz. That's for the third one. So we're going to have just 1, 1, 1, and 1. I already know how to do that. So if you are excited in the excited state, this will move to this place, move to this place, move to this place. We have something like this. So remember, in this structure, or we're going to have in this structure, we're going to have carbon-carbon. That is this carbon and this carbon, this first carbon, this second carbon. They are going to bond with each other 3 times. 1, 2, 3. They're going to have 3 bonds. Now, 2 of the bonds, if you have triple bonds, only one is a sigma bond. Take a look at that. Only one should be a sigma bond. And a sigma bond cannot be a bond between p and p orbital. Also take a look at that. P and p orbitals could form sigma bond, but they don't necessarily form sigma bond. They mostly form pi bond, because pi bond is the literal overlapping of p orbitals. When p orbitals overlap, they're going to form, unless they something like join head to head, that's when they will not form sigma bond. But in most cases, they used to form sigma bond. Think of that. So x and x orbital, which is spherical. Remember, x orbital, they are spherical in shape. They must form sigma bond. S and S orbitals cannot form pi bond. It's not possible. So please take note of that. It's still very, very important. So we're going to have 3 bonds here. So one of them is going to be formed by x orbital for both carbon. So we already have s and x here. So both of them can form our one bond, and that will be our sigma bond. Now it's already done. Then we have hydrogen here. Between one of the carbon is attached to one of the, let's just put it here for this. And the second one, we'll put one hydrogen. So this and this is going to give us sigma bond because hydrogen is s orbital and p, s and p is give us sigma bond. The next one, that's all. There's no hydrogen again. So this and this will overlap to form. Now if P and P overlap, they're going to form pi bond. This and this will overlap. If P and P overlap, they're still going to form pi bond. You can also use the structure. When we draw out the structure to run it, you see discover that the PSY and the PSZ overlaps inside the structure to form what we call pi bond. So that's how we have 1, 2. How many pi bond do you have? 1, 2 pi bond. Let's check. You have 1, 2. You have 2 pi bond. How many sigma bond? 1, 2, 3. You have 3 sigma bond. 1, 2, 3 sigma bond. So that's how we run it. That's how we run it. So there's something that we call steric number. There's something we call steric number in calculating or obtaining the hybridization of atoms inside a structure. It's still very important. Now, steric number is the number of attached atoms. Steric number is the number of attached atoms and low pair electrons. Number of attached atoms and low pair electrons. For example, if I have something like this, let's say I have something like this, let's say C. Okay, let me just draw this. I just draw. Like we said, this carbon and this carbon, they are sp hybridized. We just showed it because they have just one x and one p orbital. So they are sp hybridized, just one x and one p, and the bond angle is 180 degrees, and the shape is linear. Okay? The shape is linear. Have a linear shape on that linear shape. So let's check another way to get the hybridization of these two carbon. We can also use steric number. I'll use steric number to run it. So let's check and see if we can use steric number to run this one. Steric number is just the number of attached atom to that atom that has been attached to that atom, and the total number of lone pair electrons inside or on that atom we are looking at. So let's say we look at this one, H. See, triple bond, then H. It's a time. So what is the addition of this? What is the hybridization of this? What you just do, you just check how many atoms are attached to this. Not bond, just atoms. So we have one carbon atom attached to it. We have the two carbon atoms attached to it. So you take note. If the steric number is 2, then we are going to have xp hybridized. If it's 3, we are going to have sp² hybridized. If it's 4, we will have xp³ hybridized. That's what we're going to have, and so on. So since it's just 2 now, we have just 1, 2. This one is going to be sp², just xp. But if the steric number is 2, we're going to have xp. The same thing. How many atoms are there to this one? We have 1, we have 2. It's the sp hybridized. You can also try for this molecule, which is ylene molecule, which is a probe 1,2 diene, probe 1,2 diene, something like this. Probe 1,2 diene, probe 1,2 diene, something like this. Also, see what is the hybridization of the carbon atoms inside this compound. I just said how many atoms are attached to this? We have 1, 2, 3. So if it's 3, we have sp². How many atoms are attached to this? We have 1, 2. We have 2 atoms attached to this one. So we're going to have. Okay, finally, as you can see, for the sp³ hybridization, the orbitals involved are the 2x, 2px, 2py, and the 2pz. Then for the sp² hybridization, the orbitals involved are the 2x, 2ps, and the 2py. Others are unhybridized, like the 2pz in this case. Then for the xp, the orbitals involved are the 2x and the 2px. Those are the orbitals involved. So thank you. Okay, so this is what you're going to have. For the first example, we'll do it the steric number, and the second one. Those are the two answers. So this is our little contribution to this topic. So wish you guys good luck. God bless you all.